Welcome to Empowered Learning. The purpose of this video is to start the conversation about solving second-order linear homogeneous equations. Specifically, what this video will cover is some of the overriding properties and concepts that we need to be aware of when we solve these types of equations. Specifically speaking, the first type that we'll deal with after going over these properties will be what we call second-order linear homogeneous equations, where all of the coefficients are constant. We will eventually get into studying second-order linear homogeneous equations where all of the coefficients are not constant, and we'll study a special type of equation that's called a Cauchy-Euler equation. Of course, that won't be in this video, but just kind of letting you know we're sort of setting the stage so that we can study those two types of differential equations in particular. And then, of course, after that, the natural course of action would be to study these second-order linear non-homogeneous equations, where we basically have a second-order linear equation where the right-hand side of your equation, or the other side of your equation that doesn't have all the derivatives on it, will end up being some function, usually a function of x. So this video, again, is to sort of set the foundation and the stage so that we could talk about those types of equations and as far as techniques for solving them later. So if you've been following my videos here, you'll note that what I normally do is I will go and talk about certain concepts. I won't necessarily read these notes that I'm always showing you verbatim and then get into some examples. This time I'm actually going to do more reading than extemporaneous speaking, just because I think what I've written here will kind of set the stage for what it is that we need to think about, and it'll do it in a very efficient way here. So there will be times I will stop reading, but for the most part, I will be reading these notes that I have here verbatim, just to try to get through this concept here, because there are 4 or 5 main things that we need to talk about. But again, we need to set the stage so that we can conceptually understand what's going on before we move into solving those other types of equations that I've already mentioned. So in our study of reduction of order for second order linear ODE, and I mention that because if you're following the sets, the videos and how I'm making them, you should have studied or saw the videos on reduction of order first. Okay. So in our study of reduction of order for second order linear ODE, we noticed that this method required us to already know a possible solution to our differential equation so that we can find another solution that would satisfy that same differential equation. We also observed that by using the substitution that we're going to let the second function that we needed, a fundamental function, be a product of the first time some function u that we didn't know, where all these functions y1, y2, and u are all functions of x, that finding the other solutions we were looking for could end up being a very laborious task. So again, the reduction of order video that I've made was in 3 parts, and you saw that in those last part 2 and part 3 videos that it did kind of take a while for us to finally figure out what the other solution was. Okay. Now, our goal here is to, in this set of notes here, is to set the stage to give us some foundational tools and observations that will help us in our goal of eventually solving these second order linear homogeneous ODEs. And again, if you're following the videos at this point, what we've done is we've started the introduction to second order ODE equation solving. And so we just did it in general and said, hey, for this small subset of second order ODEs, where we can actually use substitution to figure out what the solution that will satisfy that particular differential equation would be, we'll do that. But with the second order linear ones, we have to take a little bit of a different approach to it. Okay. And so one of the reasons why we make such a big deal about it is because these types of equations are very important and they're used a lot in applications. One of the main ones that is kind of popular that it's used for is for spring mass systems. And so anything, that vibrates or oscillates and it has some kind of dampening in the oscillation, that can be modeled by a spring mass system, which is essentially going to be modeled by a second order linear ODE. Okay, so since that applies to so many things, that's why it's important that we get these properties down and we also learn how to solve these types of equations. All right, so again, our goal in this set of notes is to set the stage to give us some foundational tools and observations that will help us in our goal of eventually solving these types of equations that I just talked about. Okay. Again, these types of ODEs are very important because they arise in so many applications. Our focus for this set of notes will be on the following topics. Of course, first one, we want to be able to recognize what we call suitable choices for solutions to a second order linear ordinary differential equation. And we want to be able to figure out what the basis of those solutions are. Okay. And again, if you watch the videos that I made on reduction of order before this one, you would have heard me use this language of a basis of solutions, which is basically a fundamental set of solutions to where if I basically make a linear combination of those solutions, it will cover all of the possible solutions to that ordinary differential equation. And so we formally talk about it in this particular video here to set the stage to be able to solve those second order linear ODEs later. So recognizing suitable choices, we want to be able to discern, in other words, tell the difference in between when we have two solutions that are linearly independent versus linearly dependent for second order linear ODE. And we want to apply the principles of linear combinations of solutions and superposition to find general solutions to a second order linear ODE. Now, if you have already watched the reduction of order videos, this one you're going to naturally already know because we've already done it. Again, a lot of what I'm going to be talking about here is just to formalize everything and put it all in one place before we move forward to talk about solving second order linear homogeneous equations. The last thing that we want to talk about will be the existence and uniqueness of an initial value problem when our ordinary differential equation is a second order linear one. So basically what this boils down to here is to say, we know that with first order, if we had an initial value problem, we had one initial condition and we had one constant that we needed to solve for. Okay. Whenever we have an initial value problem for a second order differential equation, we need two initial conditions and we'll end up having two constants coming from our integration that we need to solve for. Okay. So the main idea here is that when we have those initial conditions, we're going to have unique solutions to that differential equation. So, and we'll see what that actually looks like, but just know that the main name of the game here when it comes to existence and uniqueness, if I have a second order linear homogeneous equation with two initial conditions, once I find out what those constants are from those initial conditions, that's going to be a unique or a particular solution to that differential equation given those special initial conditions. If I have a different set of initial conditions for the same differential equation, I'm going to have a different answer. Okay, and that's really what that all boils down to. Okay. All right, so we'll run through each of these topics again. And of course, the first one we'll talk about here is what does it look like to be a suitable choice for a differential equation of second order. And we're also going to talk about this concept of linear independence versus linear dependence. Okay, so we'll spend some time on that. And I'm going to go ahead and skip and get to this part here. So to talk about our study here of what a suitable solution would be and a basis of solutions, we want to consider this particular simple second order linear homogeneous ordinary differential equation. Okay. Now we see if we rewrite this equation this way, what this is essentially telling us is that if I have some function y equal to f of x, basically y is a function of x, then what I'm saying here is that if I take the second derivative of that function, then it's just going to be the negative of the original function that I started with. Okay. So for this particular ordinary differential equation of the second order, any function where if I take that function, take the second derivative of it, and it looks like the opposite of what I originally had, it would be a suitable choice, okay, to satisfy that particular differential equation. Now, if you're thinking about that, probably the first function that's probably popped into your mind would be a sine function. And if that's what you thought about, that would be correct. We know that the derivative of sine is just cosine. And of course, the derivative of cosine is minus sine, okay, which is like saying the second derivative of sine. So from there, we know that the function sine would actually be a suitable solution for this particular function here, for this particular differential equation, rather. Now, it turns out that cosine would also be a suitable solution as well, because we had cosine x. Of course, the first derivative of cosine is minus sine. And of course, the derivative of minus sine would be minus cosine. So here, the second derivative would be the opposite of the first, okay? And so both of these functions end up being what we call suitable solutions for this particular differential equation here, okay? And thus, what ends up happening is that both the function sine and the function cosine together can form what we call a fundamental set of solutions, or a basis of solutions, to where if I was to do, let's say, a linear combination of sine and cosine, plug it into this particular differential equation here after I find out what the second derivative is. Doesn't matter what the constants C1 and C2 might be when I write a linear combination of these. So let's say if I do this, this should be cosine, by the way. If I do this, doesn't matter what C1 and C2 are. If I take the second derivative of this and then stick it into this differential equation, it will still work, okay? And so in a nutshell, that's really what we're talking about here, okay? Whenever we talk about suitable solutions, basis of solutions, and trying to find a general solution from all of that, okay? So if we understand that, I'm going to kind of skip through the rest of this. You see here that I've done the whole thing with taking the derivative of sine and cosine, and notice that in both instances here, that ends up satisfying this differential equation, okay? And so again, we see here that sine and cosine are what we call suitable choices for this differential equation. And if we wanted to identify a set of corresponding fundamental or root functions that would satisfy our ODE, it would be the set with just sine and cosine in it, okay? And those would be suitable choices for that. Now, from this, we make these observations. So the functions sine x and cosine x are what we call are linearly independent solutions to our given ODE on this interval here, okay? And so this, you should say independent solutions. And in particular, they're going to be linearly independent, okay? So, and I'm saying that although here, I could just say that this is our independently solutions, because sine is a solution on its own, cosine are solutions on their own as well. but we are going to talk about this whole thing of linear independence as well. Okay, so I wanted to make sure that you understood that when I said independently here, I can actually leave that in here. So I just erased all of that so that you know that when I say independently, that just means that sine and cosine both on their own can be solutions. But again, where we're going with this is to say that, hey, these two will be linearly independent. And so I kind of crossed that out here since you had already seen an example of that. All right, so the set sine x, cosine x is called a basis of solutions for our given ODE. And again, we've already talked about that. So in general, any function that is a solution of an ODE can be classified as a suitable solution to that ODE. And any collection of suitable solutions will form a basis of solutions for that ODE. That's the main point that we wanted to get to there. Okay. Now, linear independent versus linearly dependent solutions. Okay. So we consider sine and cosine to be linearly independent solutions because in general, there does not exist a way to rewrite sine as a non-zero constant multiple of cosine and vice versa. So to kind of show that, we know that the cosine function is nothing more than a sine function, but is horizontally shifted to the left by pi over 2 units, okay? And we say horizontally shifted to the left because this x plus is translated as x minus negative pi over 2. And we know when this number here is negative, we do a horizontal shift to the left. When this is positive, we do a horizontal shift to the right. So because of this, there's no way here that I'm going to be able to rewrite cosine as a constant multiple of sine, okay? No way I can do it. So if you look here, even if I use the addition formula for sine of the addition of two angles here, you see what I just end up with in this case is just 1 times cosine, but that's not some number times sine. So this shows us that cosine cannot be written as a constant multiple of sine, meaning some number here, non-zero number times sine. Not possible, okay? Now, in the same way, we know that sine will not be able to be written as a constant multiple of cosine, okay? So that's what that's an example of what it looks like when two functions are linearly independent from each other. Now, on the other hand, if we considered, let's say, sine x and minus 2 sine x, then of course you can see here that y sub 2 is just negative 2 times whatever y1 was, okay? So this is what it looks like whenever we have two solutions that are just constant. The only difference in them is they're, constant multiples of each other. So you can divide one by the other and basically get a constant, okay? And so the thing that we want to pay attention to here is that when we talk about a basis of solutions, we're only concerned about identifying linearly independent functions, meaning we don't want anything that's in the basis of solutions that will act like these two functions do, okay? So we don't want anything that's in the basis to be constant multiples of each other, okay? Now, for general solutions to an ODE using linear independence and this principle of superposition, okay? So since the set sine, cosine in the example that we've been going over here forms a basis of solutions for this particular ODE, and the elements or functions that are in this particular set here are linearly independent, it turns out that any linear combination of these two functions, which we consider to be in the basis, be a basis of solutions for this particular ODE here, will be what we call suitable solutions as well, okay? So remember, suitable solution just means I can take that function, however it looks, do the necessary derivatives, plug into the ODE, and it'll satisfy. Okay. So I do have this note here to talk about superposition. We've kind of already seen that, but again, I'll formally talk about it here up in a second. But what I want to do now is to show here that whatever we have C1 and C2 be, this linear combination of the functions that create a basis for this particular ODE here will still be suitable, which means it'll still satisfy it. I take that by looking at two different cases of what C1 and C2 would be. So first, we're going to look at when C1 is 0 and C2 is 1, and then we're going to switch it and let C1 be 1 and let C2 be 0, okay? And so when we do that, essentially, I'm just looking at what cosine and sine are, in general. And of course, we know that cosine and sine, both on their own, are solutions. So that means that any linear combination of them should also be, okay? And again, I'm just showing the math here, why this is possible. This should be obvious to you already, but you can just take a second to look at that and see that, with those two initial conditions, still is going to work. Okay, so we're going to go ahead and move on now. So in demonstrating that C1 times sine plus C2 times cosine, it's going to be our function y here, where C1 and C2 are real numbers, is a solution to this ODE. We see the principle of superposition at work, okay? And so superposition just basically says, hey, I'm just going to take what could be the instances where I have single solutions and then just add them together, okay? And so that's what we mean by this whole any linear combination of solutions to a second order homogeneous linear ODE is also a solution to that second order linear ODE, okay? And again, back when we were doing this example here, it did not matter what C1 and C2 were. We noticed that whatever it was, our result here still ended up being 0 equals 0, okay? So doesn't matter what C1 and C2 are. The important thing is that we know what those functions are that are going to be in our basis of solutions. If we know that, to find out C1 and C2 is just a matter of knowing what the initial conditions of that particular ODE might be, okay? Now, again, with the whole point of existence and uniqueness for initial value, ordinary differential equation problems and their solutions. Again, I'm not going to get into all the mathematical detail here. I'm just going to say that if we have a second order linear homogeneous equation, matter of fact, I will even make a more blanket statement and say, if I have a second order ODE, regardless of whether it's linear or not, and I have some initial conditions with it, of course, in order for me to find a particular solution for that particular second order ODE, I'm going to have two initial conditions. And those two initial conditions are going to find specific values of C1 and C2. And when I put those specific values into the general solution, I am going to have a unique solution, okay? So that's where the uniqueness part comes from. Where the existence part comes from is that if I have a second order ODE, of course we're studying linear ones here, but just in general, ODE, if I have an initial condition to it, I know that it's going to have a solution, okay? Matter of fact, it's going to have two, okay? And we can really say that with second order linear ones, okay? All right, so because of that, I'm going to skip all this business here. All right, so to see this concept in action here, I am going to look at the same differential equation that we considered in the beginning of this video, and we're going to look at it for two sets of initial conditions. And what we're going to see is that each set of initial conditions is going to give us a different variation of a theme on a linear combination of sine and cosine. Okay. And so I'm going to skip down and just show this. So when we have this situation here, where we consider our linear combination sine and cosine, we take the first derivative here, and again, what we're doing, just in case you're not following, we are looking at this equation here and we're applying these initial conditions. Okay, so first I will need to apply this one, then I'll need to take the derivative of my function and then apply this one. So for part A, what I did is I stated the function first and then the first derivative, and now I'm actually applying that first initial condition so that I can find out what one of those two constants are. In this case, I found that C2 is 1. So now I use the derivative of my function and say, hey, when the derivative of my function is evaluated at 0, I get 2. So I substitute that information in, and I see that I end up getting C1 is 2. So C1 being 2, C2 being 1, that will be like having this be a 2 and that's a 1. That will be a specific or unique solution to our differential equation y double prime plus y equals 0. In the specific case where we essentially have, I'll just come here. Well, we essentially say that the point 0, 1 is on the graph, and then the rate of change of that function at the instant when x is equal to 0 is 2. When we have those two properties going on about the solution to our differential equation, then this is the function that models that. Okay. Now, similarly over here, we're doing the same thing. We're just taking the initial condition this basically says that I have the point pi over 2, 1 on my graph. And this other one here says that when x is equal to pi over 2, the instantaneous rate of change of my function is increasing at a rate of 2, and then you can say, by whatever units. Okay. And again, we plug in that information. We see that we get a different combination of C1 and C2, not the same as what we got here. Notice there's a little difference here. C2 is -2 here, where C2 is 1 here. C1 is 1 here, where C1 is 2 there. So you see that it's a difference. Okay. And so this note down here just says, so the initial value problems for A and B have different unique solutions based upon the values of C1 and C2 because they're different. All right, so in summary, okay, and I'm saying it this way because we're using this particular ODE as an example, but after we go through all the summary of all the points that we want to make for this particular ODE, what we're going to do is kind of fall back and say, all right, well, let's make a blanket statement about equations like this as well, okay? So for this particular ODE, we saw that the functions sine and cosine were what we consider to be suitable solutions because both of these functions satisfy this ODE, okay? And we know that because of that, these two functions form what we call a basis or a fundamental set of solutions for this ODE, okay? Now, we know that the functions sine and cosine in our basis are what we call linearly independent, and that is because we cannot rewrite sine or cosine as a non-zero constant multiple of each other, okay? The third thing here is that sine and cosine are linearly independent of each other. Because of that, it follows that any linear combination of both of these functions that are in our basis, which we'll write it like this, will also be a general solution of this particular equation here. And then, of course, if we had some initial conditions to our second order linear homogeneous ODE, then the initial conditions of normally would look like this, okay? And I did it this way to keep it general, but most of the times what you will see is something like this. So you'll see, you'll have some X value and let this be a corresponding Y value. And then here you'll have the same X value, but you'll have something different here. So I'll just call this Z1, okay? The point here is that most of the times you'll see problems where these X values will be the same, but they can be different. And so that's why I wrote it this way, so that you'll know, hey, it doesn't always have to be that we have the same X value here and the same X value there, okay? Now, in some of the extreme cases, it really just depends upon what you know. You could also have instances to where, let's say you have Y is equal to, let's say Y of X1 is equal to Y1, and Y of, let's say, X2 is equal to Y2. So my point here is that we could just have information about the original function and nothing about the derivative and be able to find out those initial conditions, okay? Or we could have instances to where we just have information about the derivative in two different places, okay? All of that is possible, but traditionally speaking, we like to have information about the original function and the derivative of it both at the same point, okay? And so that's why, again, when you see problems normally in a first year differential equations course, that's why most of them sort of end up looking like the ones that you see here, okay? Now, everything that I have here is just, me trying to do my preciseness with the math mumbo jumbo or whatnot. But if you understood what I said here, that's pretty much all you needed to know, okay? All right, so now if we went over those 4 points for the ordinary differential equation that we were working on. So this, what we call big theorem for second order linear homogeneous ODEs, is sort of the catch-all to say, all right, well, it doesn't matter what type of ODE you're talking about, as long as you're talking about a second order linear homogeneous one, all these things will be true, okay? So first, this says let X be in between two numbers, alpha and beta, and you just want to simply think about this as the domain of your function Y, okay? And so Y is going to be a function of X. These values will be in the domain of that. So meaning I plug in these X values, I will get corresponding Y values that will be real numbers. So all the X values in here are going to be defined for that. So that's pretty much all I'm saying. So if we consider that situation to be a solution to a second order linear homogeneous ODE, and of course, this is what that would look like. And remember, again, it's homogeneous because it equals 0. And remember that our coefficients A, B, and C can either be constants or functions of X, okay? And in the subsequent videos, we're going to first talk about A, B, and C all being constants first. And then afterwards, when we start to talk about the Euler-Cauchy or Euler equations or Cauchy equations, depending upon how you want to say it, then we'll be talking about ones where we have just functions of X as the coefficients, okay? So if we have all that in place, then we know that following are true. 1, we have at least one basis of solutions that will exist for this particular equation here, okay? So we know that has to happen. We know that every basis of solutions will consist of a pair of function solutions. And the reason why it is a pair is because we're dealing with a second order ODE. So second order means two functions in the basis of solutions. If I have a first order, then that's one function in the basis of solutions. If I have a third order, I have 3 functions in the basis for my solutions, okay? Now note here that this y equals 0 solution is what we call a trivial one, meaning that all of these equations of this ilk here will all have y equals 0 as a solution. So when we talk about this, the existence of solutions or whatnot, we're really not talking about the trivial one, okay? So this really should be, we have at least one basis of non-trivial solutions, okay? Because we know if I let y be 0, then the derivative of 0 is 0, and the second derivative of 0 is also 0. So well, we already know that works, okay? All right, so the third topic, if a fundamental set of solutions, aka basis of solutions, contains y1 and y2 that are linearly independent, then that means that the general solution can be expressed as a linear combination of those two functions that are in our basis, okay? And of course, C1 and C2 will be real numbers. Now, last point, for any x value that's going to be in the domain of our function that we're considering the solution to the ODE to be in, and any two fixed values a and b, if we consider that as well, that are not necessarily required to be in this particular range here, meaning x values that's going to be in the domain, but it could be, there's going to exist exactly one pair of constants C1 and C2 such that, again, y is going to be a solution for that, and it will also satisfy these initial conditions. Again, this is just a fancy way of saying that if we have two initial conditions for a second order linear homogeneous solution, we're guaranteed, second order linear homogeneous ODE, we are guaranteed a unique solution to that particular ODE based upon these two initial conditions, okay? All right, so I know I've said a lot of stuff over and over and over again, but again, we want to make sure that you get these basic concepts down because as we go deeper into solving these types of differential equations that I've mentioned earlier, we need to have these things in mind so that the work that we do to solve these solutions all makes sense. All right, so now we're going to get into some examples here. And so for the first set of examples we have, we're going to be given second order linear homogeneous ODEs, and we want to do the following. We first want to verify that each pair of functions that we're given is actually going to be a fundamental set of solutions, aka it's going to be a basis of solutions for the ODE. The second thing that we want to do is find a linear combination based upon these two functions that are in the fundamental set, okay? And by default here, if we verify that each of these functions are going to be a fundamental set of solutions, another part of that is making sure that they are linearly independent, okay? All right, so for our first example here, here is the ODE. So notice that it's a little different than what we had before because I had plus here before, but now got minus. And now we are considering that sine hyperbolic, cosine hyperbolic, or sinh and cosh of x are going to be suitable solutions for this particular ODE. And so what we want to do is see that both sinh and cosh x are going to be solutions on their own, okay? So for this first one here, we see that sinh of x, or sine hyperbolic of x, if we take the derivative of that, it's going to be cosine hyperbolic. And of course, if we take the derivative of the derivative, it's going to be sine hyperbolic again, okay? With the hyperbolic functions, we don't have the minus sine hyperbolic like how we would if we were just doing the derivative of cosine, which would be minus sine. So it's a little different there, okay? All right, so here we see that the second derivative is the same as the original function. So we take the difference of those two, of course, we get 0. So we know that sinh x is going to be a suitable solution to this ODE. If we repeat the process with cosine hyperbolic, or cosh x, then of course we see that, again, the original function and the second derivative are the same. Plug them in to our ODE here and here, and we get 0. Okay. And of course, if we do a linear combination of these two, it's going to look like this. And we know that this could be a general solution of this particular ODE. Okay. Now, on the next page here, one of the things I note is what sinh and cosh x actually mean. And remember that the sine and cosine hyperbolics are just a linear combination of exponential functions, e raised to the x and e raised to the negative x to be exact. So part of the reason why I'm showing this here is that we are going to need to have this information to apply the initial conditions, but also note that this function and this function, they are not, these two functions here are not what we consider to be linearly dependent. So in other words, I can't rewrite this function and this function as a constant multiple of each other. Okay. So it looks like it could be that way, but because of this minus and this plus here, that wouldn't be possible. Okay. All right, so here we also see that if I take the original function or the original general solution here and I write it in terms of its exponential equivalent here, I have y, and then of course I take the derivative of that, I'll get that. And so we put it this way so that we can actually apply these initial conditions here, and we're going to find out that if we have it in this exponential form, it makes it easy for us to evaluate this particular function or this particular general solution using these initial conditions here. So our first initial condition, I'll go back up here just so that you can see that it was stated there. This was our first initial condition. This is our second. And for this one, this should be y prime of natural log of 2, not just y. So coming back here, we see that y of natural log of 2 is equal to 1. Everywhere where we see x in this particular function here, we replace it with natural log of 2. And of course, it's going to equal 1 in this case. So you see, I'll go ahead and plug in everything. And notice that negative natural log of 2 is the same as positive natural log of 1/2. Okay, because we're just taking that understood -1, putting it in the exponent there, and 2 raised to the -1 is the same as a positive 1/2. So once we do that, then of course, using our logarithm properties, e raised to the natural log of whatever is just whatever. So you see that I'm doing that for each of these terms here. And then it's just a matter of rearranging everything. And we see that we get one equation here where we have 2 unknowns. If we do the same thing for our second initial condition, we take the derivative of y, which is this function here, plug in natural log of 2 everywhere where we see x. We get this result here, have that equal 6. And then, of course, again, we know that e raised to the natural log of 2 is just 2. E raised to the negative natural log of 2, or e raised to the natural log of 1/2 is 1/2. And we repeat here. And then it's just a matter of some computation to get this second equation where we have 2 unknowns. So 2 equations, 2 unknowns. We could use systems of linear equations to solve for what C1 and C2 are. And I won't bore you with the details on how to do that, because I'm assuming that if you're watching this video, you do know how to do that. But here you see that I've used the addition method, or I think some people call it the elimination method, to actually do it. And we see that C1 is 27/4, C2 is -13/4. And so this will be our unique solution to the differential equation that we started to work on, which was this one, under these specific initial conditions. All right, so again, this is our unique solution to our ODE based upon the two initial conditions that we had here. All right, so let's move on to the next example. So this one we'll actually work through together. So we're told here that we need to consider cosine of 2x and sine of 2x as being functions that will be suitable solutions to this particular ODE under these initial conditions here. And so the fact that we have these two initial conditions means that we are going to find a particular / unique solution to this particular ODE. So the first thing that we need to do is verify that each of these functions are solutions on their own. So I'm going to say verify y1 of x is a solution. So we'll do that first. So here, I just need to find the second derivative. So y1 prime here will be minus sine of 2x times 2 via the chain rule. And second derivative would be minus cosine of 2x. And of course, I already have this 2 here, but then I need to take the derivative of the inside function again, and that's going to be that. So this is minus 2 sine of 2x, and this is let's see, yep, I did that wrong. Because if I take, no, I did that right. So, because we started off with cosine. Yep, that's right. So this will be minus 4 cosine of 2x. Okay. So therefore, if I do y double prime of 1 plus 4 times y1, does that equal 0? And we know that y1 double prime is minus 4 cosine of 2x plus 4 times y1, which is cosine of 2x. That indeed does equal 0 because both of these cancel out. Okay. So, you know that's verified. We'll do the same thing over here. Verify y2 of x is a solution. So again, y2 prime, this will be 2 times cosine of 2x using the chain rule. Y sub 2 double prime will be a minus 2 times 2 times sine of 2x, which is just a minus 4 sine of 2x. And again, that's in using the chain rule again. So therefore, we know y2 double prime plus 4 times y2. Does that equal 0? Plug everything in. Minus 4 sine of 2x plus 4 times sine of 2x. And that indeed equals 0 again, because the left side, both those terms cancel out. All right, so we have figured out that both y1 and y2 are both solutions on their own, okay? So the next thing that we need to do is say, hey, well, because of that, what is going to be a general solution that we can write for this, okay? So here, therefore, I'm just going to put general solution here. So general solution would be y is equal to y of x, which is going to be c1 cosine of 2x plus c2 sine of 2x, okay? And so that would be using what we know about both sine of 2x and cosine of 2x being functions that are linearly independent of each other, okay? we know that those two functions, since they also are solutions of the differential equation on its own, can be considered to be suitable functions to form a basis of solutions for our ODE. And our general solution includes the family of all possible solutions to the ODE that we're working on, okay? And so, of course, to figure out what C1 and C2 are, we're going to need to apply the initial conditions so that we can find out the specific member of the family of this ODE that we're trying to find a solution for that has those properties in mind. Meaning, here's our general solution here. We want a function that looks like this, to where the point 0, 2 is going to be on the graph. And at the same time, the instantaneous rate of change of this function when x is 0 is going to be 6, whatever units. Okay, we can say meters per second or whatever. Okay, since we don't have that information, we won't worry about it. So with this initial condition, we can go ahead and use what we have here. But I'm going to go ahead and solve for or evaluate what the first derivative will be, because we're going to need that info too. So here, if we took the first derivative of this would be a minus 2c1 sine of 2x. And over here, this would be 2c2 cosine of 2x. Okay. And go ahead and draw a line here just to get some separation. All right, so switch colors again. So here, everywhere where we see x, we're going to put a 0 here, and then of course it's going to equal 2. So if we have this situation here, this is just c1 cosine of 2 times 0 plus c2 sine of 2 times 0, and that's going to equal 2. Now, we know here that sine 2 times 0 is 0, so sine of 0 is 0, so this whole entire term here will be 0. And here we know that cosine of 0, because 2 times 0 is 0, all of this is just going to be 1. So what that shows us here is that C1 is going to be equal to 2. Okay. Do the same thing here for the first derivative. So we have minus 2C1. Oops, that didn't turn out real good. So C1. And this will be sine of 2 times 0 plus 2c2 cosine of 2 times 0. And again, we know that sine of 0 here is 0, so this whole term goes to 0. This goes to 1. And from the initial condition here, we have to make all this equal 6. So that means here that 2c2 is equal to 6, which means that if we divide both sides by 2, c2 is equal to 3. And so now from here, what we know is that our particular, I'm going to say particular unique solution to this ODE will be y of x is going to be equal to C1 is 2, so it's 2 cosine of 2x plus 3 sine of 2x. Okay. Now, this is a particular solution because we know what C1 and C2 actually end up being. It is a unique solution because this will be the only solution to our differential equation that will have both this property and that property at the same time. Okay. So I don't want you to think that particular and unique mean the same thing. They don't. But of course, they can go together to describe what type of solutions we have. Okay, so we're going to do another example where we work everything out here, but I kind of want to give you some context on what these examples are trying to do. So if you notice here that for this example, we do have a second order linear homogeneous ODE, okay? Highest derivative is a 2, so that makes it second order. We have second derivative, first derivative, no derivative, and then that's it on the left-hand side. And of course, homogeneous because it equals 0. Now, notice in the previous example that we've done, and I'll go ahead and skip back up to that. Notice that in this example, we also had a second order linear homogeneous ODE, but here our coefficients, the understood 1 here and the 4 here, and we had a y prime term that was missing, had a understood 0 there. Notice that all of our coefficients were constant, okay? In the example that we're going to be doing now, all of the coefficients are not constant. So we're seeing, we saw an example here of how this all works whenever all the coefficients are constant. Now we're going to see an example when the coefficients are not all constant. All right, so again, we need to first verify that y1 is a solution, and we're going to do the same thing with y2. So verify y2 is a solution. Okay. So for y1, if I take the first derivative of it, that's just going to be 2x. If I take the second derivative of it, it's just going to be 2. And so now I just need to plug that information into this equation here. So therefore, I'll have x plus 1 quantity squared. That's y double prime minus 2 times x plus 1 y prime plus 2y equals 0. That implies here for the y double prime, that's just going to be 2. For the y prime, and remember this is y sub 1, y sub 1, y sub 1. So y prime, we have 2x. And we say plus 2 times y1, which is going to be x squared minus 1. That didn't turn out right. And all that's equal to 0. And so now we just need to work this all out. Make sure that the left side is equal to 0 there. So here, trying to think, yeah, I think I probably need to just multiply all this out. So this x plus 1 quantity squared is just going to be x squared plus 2x plus 1. And all that multiplied times 2. Minus, here I have this 2 times 2x, which would be 4x times x plus 1. And then here, this will be 2x squared minus 2. And we're saying, does that equal 0? Okay. So continuing on, distribute this 2 to all 3 terms there. And then we'll have minus 4x squared minus 4x plus 2x squared minus 2. Does that equal 0? Okay. So now if we look here, first thing I see is that I see that 2x squared and another 2x squared here will cancel out with minus 4x squared. So all 3 of these will go. I see a 4x and a minus 4x that will cancel out. And I see a 2 and a minus 2 that will cancel out. So we do see that y sub 1 does satisfy this ordinary differential equation. We'll do the same thing with y2 now. So y2 prime, the derivative of x plus 1 is just 1. And the derivative of y2 double prime is 0. So again, we have our equation here, and this is y sub 2 now. Is this going to equal 0? Well, we know for this first term here that all that's just going to be multiplied times 0. For the second term, it'll just be multiplied times 1. And for the last term, this will be x plus 1. And does all that equal 0? So from here, we know that all this is just 0, so we forget about that. So, and this is just 1, so this will be just minus 2x minus 2. And this will be plus 2x plus 2. Does that equal 0? And of course, these two terms here cancel out. These two terms here cancel out, and it works. Okay. All right, so we have officially verified that x squared minus 1 and x plus 1 are two functions that are going to be linearly independent of each other. And we say linearly independent because, again, these two functions cannot be written as constant multiples of each other. To kind of show you that, let's say if I took y1 and divided it by y2 here, we know that x squared minus 1 here is just x plus 1 times x minus 1. And notice that these two terms would reduce to 1, but the result here is a function, not a constant. So because of that, we know that these two functions here are linearly independent of each other. So now that we know that, then of course, for our general solution here, we know that, of course, the functions x squared minus 1 and x plus 1 are going to create what we call a basis of solutions for our ODE. And thus, we know that C1 times x squared minus 1 plus C2 x plus 1. This would be a function to characterize all of our possible solutions for this ODE. And so now we can just use the initial conditions that we were given here. And I'll circle them here because I know I got a lot of writing going on. So these two initial conditions here to find out what our C1 and C2 will be. All right, so here, first initial condition. So we take our equation here, and well, before I do that, let me go ahead and take the first derivative since we're going to need that as well. So I'll take that, and so the derivative of x squared minus 1 will just be 2x. This will be 2c1x here. And of course, derivative of x plus 1 here will just be 1. So our first derivative will be this. So now that we've taken care of that, now we can use this function here. So we have c1, and where x, I'm going to put a 0 there, plus c2, 0 plus 1, and all that equals 0. So again, we're just putting 0 everywhere where we see x. And then, of course, here we're making the actual, this side equal 0 over here. And if we do that, then, of course, this just means that 0 squared minus 1 is just minus 1. So this is minus C1 plus C2 is equal to 0. And what this tells me here, if I add C1 to both sides, is that C1 and C2 are the same, whatever they are. Okay. All right, so now let's look at our initial condition, the second one, which was a derivative of our function at x equals 0 is going to be 4. And so now we'll say 2c1 times 0 plus c2 is equal to 4. Well, that makes it real easy because all of this is 0. So that means c2 is equal to 4. And that implies that c1 is also 4. And so what that means for us here is that therefore our particular and unique solution will end up being 4 times x squared minus 1 plus 4x plus 1. And of course, I could simplify that if I wanted to. So this would be 4x squared minus 4 plus 4x plus 4. And these two terms cancel. So I would just have 4x squared plus 4x. And that would be my particular and unique solution to this particular differential equation under these two initial conditions here. All right, so I have one last example that I want to go through, and I'm going through this one just because it's a little bit more interesting than the other two, last two that we've done. We have a little bit more involved in taking the derivatives and whatnot, but I want to show you that it doesn't really matter the difficulty. The concept is still the same. Okay. Now again, we are dealing with a second order linear homogeneous ODE because of course we got second derivative, first derivative, and no derivative terms here. All of our coefficients are either constants or functions of x, and of course the right hand side of our equation is equal to 0. And so we see that we have our two initial conditions here, and we are considering that cosine of x squared and sine of x squared are going to be our functions that create a basis of solutions for our ODE, and we just want to verify that. So as you see here, we take cosine of x squared, take the first derivative, and then take the second derivative. And of course, going from the first derivative to the second derivative, we would have to end up using the product rule here. So that's how we end up getting two terms instead of just one. And then again, we just plug in everything. So we know that y double prime is just going to be all this. We know that y prime is just going to be this. So you see how we plug in y double prime here, y prime here, and then what y is. And of course, you do all the algebra to work everything out. And you see that what we end up having here is that we got all terms essentially canceling each other out. Okay. And so if we do the same thing for sine of x squared, well, we'll see a similar sort of thing happen here. This is our first derivative using the chain rule. And going from first derivative to second derivative, we have to use the product rule and the chain rule. And so we take that, substitute in y sub 2 double prime here. Substitute in, y sub 2 prime here. And then y sub 2 there. And again, you see that if we, distribute the x and distribute the 4x cubed in the first and last terms respectively, work everything out, we end up getting that the left side equals the right side. And so again, that lets us know here that our function y of x can be considered a general solution for the ODE that we're working on. And here I just found the first derivative of this particular function here so that we could use it for our initial conditions so that we can find out specifically what C1 and C2 are. So our first initial condition, I elect to use the first derivative first just because I guess it felt like it was easier for me to solve it that way. Here, let me think I should have a prime right there. Don't really know why it's missing, but it should be there. So I elected to work on the first derivative first. so I did that, and everywhere where we saw x, we put in the square root of pi. Everywhere, and of course, it all equaled -4. So we did this business here. Of course, square root of pi squared is just going to be pi, and sine of pi is going to be 0. And same deal with cosine. Square root of pi squared is pi, and cosine of pi is -1. So from that, we see that this whole first term here goes 0. All we're left with is what this second term is. And then, of course, we just solve for C2. So C2 ends up being a -2 divided by square root of pi. If we continue on, we can use this information of what C2 is and our initial condition of y of square root of pi is equal to 3 to figure out the other one. Okay. And so for here, we notice that if we do it that way, we get lucky here in the second term, since we have a sine of square root of pi squared. And of course, the inside here just ends up being pi. Sine of pi is 0. So this term gets eliminated, and we just have to work with this one. And we see here that C1 just ends up being a -3. And then we let C1 be this, let C2 be that, and we are done. So we have a particular unique solution for our ODE. Okay, and you see how we got that using those initial conditions. All right, so just to try to summarize everything before we leave and we get into studying second order linear homogeneous equations where all the coefficients are constant. That will be the next video that you should watch if you're kind of following these in order. So notice here that because of the fact that we knew we had a second order linear homogeneous equation, we knew that we had to have two functions to be able to form a basis of solutions for us, for our ODE. Okay, and we know that if we were given initial conditions, that we had to have two of them to go along with the two basis functions or fundamental set of solutions functions, so that we can characterize our general, let me say that again. So we essentially had two functions for this second order linear homogeneous ODE, and they served as a basis of solutions for this particular ODE. And that just means that any linear combination of those two would actually end up being a solution themselves. And of course, the two initial conditions allowed us to be able to find out a specific C1 and C2 out of that whole family of possible solutions that we had. And of course, in this case, what we found is a particular solution, meaning that C1 and C2 were found, and a unique solution because this is the only solution here that will have the properties that y of square root of pi is 3 and y prime of square root of pi is going to be 4. Okay. All right, and so all these things that we've talked about here, I know it seems like if you've watched my other videos, we've kind of gone over all these things before, but we're kind of putting them all in one place because we'll need to think about all this as we move forward and talk about solving more second order linear ODEs.